The next two lectures are also going to be a continuation on the same theme of network flows, and our main goal here is one to first see some of the properties of the Ford-Fulkerson method that we have looked at. We are going to revisit a few things, and then we are going to look at applications. As Professor Narayan Swamy said early on in the lecture, it has several applications to several problems, and we are going to in particular look at certain problems and reduce it to a network flow problem, which will allow us to solve those problems that we would like to as just a black box application of a network flow problem, right. So before we go into that, I would like to revisit the Ford-Fulkerson method and ask a few questions, right. So what did we do in the Ford-Fulkerson method? Can somebody remind me? So we have been given a directed graph G. So it was called D, but I'll just call it G, GVE, which has a capacity associated with every edge, and we have two designated vertices S and T, and our goal was to ship as much flow as possible from S to T with the constraints, that is, for every edge you cannot send as more flow than the capacity of the edge, and at every node other than S and T the flow must be conserved, that is, inflow inside to the node should be exactly equal to the outflow for every other node except S and T, right. So I have the following proposal. So so let me just ask, what did we do in the case of the Ford-Fulkerson method? We have just seen it just now, so can somebody recall what we did? It was an iterative procedure, and in each iteration we did something. So what did we do in each iteration? So we have a current flow, which we are calling it as F, and with respect to the current flow we did something. What did we do? So we computed first the residual network. So let us focus on that step of computing the residual network. So if you have a flow function F, remember always that the flow is a flow function, that is, it assigns a value, we'll assume integer capacities, and therefore it also assigns integer values which are non-negative to every edge in the graph, and this is a function, right. So we have a flow function uv for every uv belonging to E, which is less than or equal to CUV and which is greater than or equal to 0, right. This is what we have. So we have this flow function, we defined a residual network. So can you elaborate how did we come up with the residual network? So if you had an edge UV and you sent a flow FUV on that edge, then you defined the residual capacity of that edge, which was defined as CF of UV is equal to C of UV, which was the original capacity, minus F of UV. This was the residual capacity of that edge. Is that all the edges that are present in the residual network? So for example, let me just draw this simple example. So I have this simple flow network S, A, B, T, and I have a unit capacity on every edge. So I will not write down that, and let me say that I have a flow. So typically it is customary to write in the flow networks as I have sent 1 unit on this for which it had a capacity of 1. So this 1 over 1 says that the flow value F of SA is equal to 1 and C of SA equal to 1. This the by 1 in the later part says that this is the capacity. Similarly, maybe I sent 1 unit across this and I sent 0 unit across this, 0 unit across this, right. So this could be the way I would have sent my flow. Is this a valid flow? This is a valid flow, right. So let us ask, what is the residual network with respect to this flow? All of us have studied this in the previous lecture. So let us ask, what is the residual network? This is the flow F. So I will construct a residual network S. The vertices remain the same, right. So I will just draw the vertices first, and so please help me how to draw the edges. So what should I draw from S to A? We do not draw any edge from S to A, right. Okay, so we will leave the S to A edge as not drawn. What about A to T? In a similar spirit you will not draw because it has flow equal to capacity. What about S to B? I will draw the same edge with capacity 1, and I will draw the same edge B to T with B to T with capacity 1 again. Anything else that I should draw? A to B again with capacity. Is this the residual network? That is 1, right? And again I should, in a similar spirit, I should give possibly from T to A the capacity of 1. So this is actually the residual flow network. So what does it say? For every edge which is present in the original network, you have an edge which is in the same direction, which will have capacity which is equal to C of uv minus f of uv, and you retain that edge only if the capacity happens to be greater than 0, otherwise there is no point in retaining, and that is why we deleted this edge. Similarly, you will also have an edge from if uv was present in the original network, uv belongs to E, then you will have an edge Vu in GF with C of Vu equal to f of uv, right? That's all, f of uv. And again, on this is useful only if so I should simply say Cf of Vu is equal to f of uv, and this is again meaningful only if the residual capacity happens to be greater than 0. For example, B to S also we could have had an edge, but that would have a residual capacity 0 because the flow along that edge is equal to 0 in F, right? Okay, so this everybody understands what is the residual network. In fact, you will be asked to construct residual networks for a slightly more complicated graph and a slightly more complicated flow in the exercise sheet. But now my claim is, why do we do all of this? Maybe we should, why do we have this residual edge? I mean, this I understand, there is a residual capacity. So if you had a forward edge in this, in the case where you had an edge S to A, and suppose it had capacity 2, you have a residual capacity of 1 which is remaining, and you are encoding that by putting an edge of this value Cu of uv minus f of uv. What does this edge, which is a which was not even present, what does it allow us to do? For example, maybe I should have just not had these edges, and still I would have computed an ST path and got the, so what is the max flow in this network? Let us observe this network. So this is the network I am referring to. What is the max flow value? 2 units, right? You can send 2 units because you can route S to A to T and S to B to T, and that will give us 2 units of flow, correct? And currently I am sending 1 unit, which is not the max flow, but you can clearly increase the value by looking at this network which did not even have these edges, right? So suppose I did not have these edges, this still is a valid thing, right? So why have these residual edges? Okay, so let us make the thing interesting and see that what did our Ford-Fulkerson method say. First, so when we began our algorithm, actually the flow on these edges should have been 0, right? There was no flow associated with these edges. So the residual network is exactly equal to the original network, right? Now there is no change in the residual network. That is, this same network forms our residual network. So then it said that find an ST path in the residual network and send flow as much as you can along that path. That is actually determined by the edge having the smallest residual capacity on that path, right? So what I will do now is this, because this is my flow network, and with respect to the 0 flow, this is exactly equal to the residual network. I will choose the path which is S A B T, right? So is that a valid path? It goes from S to A to B, and B to T, right? Let us do that, and I will send 1 unit of flow along that. So now my picture has changed, my flow is also changed. So 1 over 1. I hope everybody is comfortable with this notation of 1 over 1, which just says that I am sending 1 unit of flow along this edge, and the capacity is also 1 unit. So this is my new flow. We could have called it, this is S and this is T. We could have called this flow, let us say F prime, right? And I can also compute GF prime. So what is GF prime? I will, so I will just, maybe I will use another page and I will recall the network. right. So let us compute the residual network with respect to this according to my new definition, right. Let us compute the residual network. So what will I do? Will the S to A edge survive? No. And I said that okay, if it doesn't survive, just don't worry about it. So I will not have nothing. What about A to T? Will it remain? It will remain, right, because I did not send any flow. So I would send 1, it will have a residual capacity of 1. What will happen to the edge S to B? It will again survive in the residual network, it will have a capacity of 1. Those are the only edges that will survive. In this path, in this network, there is no ST path, right. So this seems to be a problem, right. We have sent only 1 unit of flow and still disconnected all ST paths, right, and this seems to be a problem because how did our algorithm proceed? It said as long as you have ST paths in the residual network, keep finding them, augment the flow and compute the residual network again, right. So then let us now try. So this was an incorrect residual network. And now let us see what we have seen in the class to begin with. Let us see what the residual network would be. Again, will the edge S to A survive? It could have been there but with 0 capacity, so we will delete it. So what edge will be present according to the way we have discussed in the morning? A to S with capacity 1, residual capacity 1. Again this edge will survive with capacity 1. What about the edge A to B? It has a flow of 1, it will not be there, but there will be an edge from B to A which has capacity of 1, and this edge will have capacity 1 and this edge will be again reversed and will have a capacity of 1, right. So this is how our residual network, the correct residual network looks like. Now what can you, so now is there a ST path now? There is indeed an ST path which is SBAT, and along that you will send 1 unit of flow. And now remember, so this flow F, this was what we called as our flow F prime, right. When I write F prime, you should also write F prime of SA equal to 1, F prime of SB equal to 1, F prime of SBT equal to 1, and for everything else it is 0. So I will just write down F prime of SA equal to F prime of AB equal to F prime of BT equal to 1, and F prime of everything else xy is equal to 0 for all xy. So this is the way F prime is defined. Now what is what is the flow in the residual network, which we had actually called F prime, but I will just call it some other F double prime now. What is the flow in the residual network? On what edges does it send flow? S to B, B to A, not A to B. F double prime of B to A is A to T, F double prime of A to T is equal to 1, and again F double prime of all other things is 0, right. And how did we actually combine these two flows? You remember we had written F augmented with F prime, but I will now have to write F prime augmented with F double prime of UV, right. And this should be defined only on the edges of the original network. So let's try to define this for the edge SA. So it is equal to F prime of UV plus F double prime of UV minus F double prime of VU. This was how it was defined, right. So let us try to substitute this for a couple of things so that we understand it correctly. So let us do this for the edge SA, and what will we get here? F prime of SA, it is written here, it is equal to 1 plus F double prime of SA, it is equal to 0, because actually that edge is not even present in the residual network. It is 0 minus F double prime of AS if you sent any, which you did not send, because here you are going to send a 1 over 1 on these edges, right? This is what you have. Is this fine? So this is minus 0, which happens to be 1. So the augmented flow along this edge continues to be 1 unit. That is what it says. Now let us do it for the interesting edge, which is f prime augmented with f double prime on the edge. Which is the interesting edge? AB, right? That is the interesting edge. And let's look at what happens. We had 1 unit of flow sent in this, which is on AB, plus did we send anything in the direction A to B in f prime? No, we would not have, and that is 0. But then we have sent 1 unit back on B to A, which is what it is subtracting, and therefore it happens to be 0. Right? So what this says is that in the final augmented flow, you are going to have flow along SA, AT, SB and BT, and no flow along the edge AB, which is what you would expect, right? And this is what this formula allows us to do, and in fact what this allows us, these residual edges that have been very crucially introduced, these edges wherever you had a flow of FUV units, you have introduced a VU edge and given the residual capacity as FUV. Those are very crucial in making sure that if you made a mistake in finding a path, you are able to correct it eventually, right? So if we actually took a path which was SABT, then you are able to correct it and get to the correct max flow. So these residual edges are very crucial. You cannot go with this simplistic idea of, okay, if I have an edge and if I send FUV units of flow, I simply subtract that and do not add those reverse edges, right? Are there any questions or any other suggestions to possibly avoid this kind of residual edges? So I just wanted to emphasize this point, that this computation of the residual network is very important, and these residual edges play a very crucial role in the in actually getting to max flow. I mean, otherwise we would have had a network which was disconnected and we would have stopped at 1 units of flow, which is not the correct max flow. Okay, so let us take this example a little further, and let us ask, how long does this Ford-Fulkerson method take, assuming that we have already argued that the Ford-Fulkerson method terminates because there is a bound on the value of the max flow which is exactly equal to the min cut of the graph, and therefore it is going to terminate, and it will take several iterations. So we have to count how many iterations does it take and what is the cost of each iteration. If we count that, then we are going to get a running time upper bound for the Ford-Fulkerson method, right? So what is it that it requires to do every iteration of the Ford-Fulkerson method? I do not have that template here, but I hope you remember that. So it is like compute the residual network, find an ST path in the residual network, modify the flow, and then call that flow f prime as f, right? This is what you did. So how long does each step take? So for example, how long does computing the residual network given a flow take? So what does it involve in computing the residual network? Good. So you go to all pairs of vertices, ask, is that edge present? If that edge present, does it have a flow? If it has a flow, then add the residual capacity in the forward direction, add the reverse edge and set the residual capacity accordingly. So this is for every edge you are doing some constant amount of work, right? So I will write that computing the residual network takes order m plus n time, right? Good. Now what does it require us to find an ST path? How do you find an ST path in a directed graph? Because now it is a simple directed graph. You just did not ask for any special path. Find any ST path. How long does it take to find any ST path? Order of n. Can you do it with so does DFS require only order of n time irrespective of the number of edges? M plus n, because it does visit every edge exactly twice. So then computing an ST path in GF requires again an order m plus n time. Okay, good. Now what is the next step? Once you have computed the ST path can be only order n long. I mean, it can only have n edges because it's a simple path, and therefore you have to simply pick the minimum weight, minimum capacity edge on that path, set that to be equal to your flow, which is your f prime, and then do this computation of f augmented with f prime. How long does this take? So this is a new flow, right? We had called this a new flow. So this we have to again compute. How long does it take? Yeah, so again we will simply say that it takes order m plus n time for the computation of this augmented flow, right? And then you just set f prime is, that is only a constant, this thing, right? So we have some linear amount of work done in the loop, inside the loop. Now the question is, how long does this loop take? How many loops are you, or how many iterations are you going to take? This is the question. So how many iterations? So we will again have the same example. So we have actually, I will not write flow, I will just write capacity. Or right. Right, so the structure of the graph remains the same, but the capacities have changed. So what have I done? I have given all the 4 edges a capacity of 2000, right? And what is the max flow in this network? 4000 units, because I can send 4000 units of flow, right? But now let me do the bad thing for your algorithm. So what I will do is, every time I will choose the path, it's the adversary gives you an SABT path. So how much units of flow can you send along that? 1 unit. Now the next iteration, the adversary again chooses for you the path SBAT, because you ask them to choose one path, right? And it keeps on giving you this path, right? And therefore, how long will this algorithm take to terminate? Each time you are increasing the flow by 1 unit, how long will this algorithm take to terminate? 4000 units, right? 4000 iterations, because every time it starts with 0, it has to terminate at 4000. Every time it increments by exactly 1. So it takes 4000 iterations for you to actually compute the flow in this flow network, right? And this 4000 is just one number, right? I could have made this something like very large, 2 to the power 2000. I could have made all these capacities 2 to the power 2000, and this bad execution sequence will require 2 to the power 2000 on a constant size graph, right? So it has nothing to do with your graph size, and but it has to do with your capacities, right? So this Ford-Fulkerson template is a very good method, is a good template. It gives you a correct algorithm, but it need not always lead to an efficient algorithm, right? So what we can clearly say is that if f star was the max flow in the flow network, and this is the value of the flow, the max flow, that is value of f star, then f star into order m plus n is a valid running time, right? Because you cannot take more than f star into m plus n. Each iteration of Ford-Fulkerson method allows you to increase this thing. So this is a little imprecise. You have to say that on networks which have rational edge capacities, we are actually treating even a special case which has integral edge capacities, and we have been saying that all the flows that we compute by the Ford-Fulkerson method are going to be integral flows. So as long as we are under that restriction that we have integer flow capacities or rational flow capacities, we are still okay. The Ford-Fulkerson method is always going to terminate, and it will terminate in the value of f star into order m plus n many iterations, right? But as we have already seen, this value of f star may not actually be a good number. Good meaning it may be a very large number. It is good for the flow network, you can send large amount of flow, but in terms of the running time of our algorithm, it is not an efficient algorithm, right? So in the coming lectures tomorrow, you are going to see possibly an efficient way to compute a max flow in a network, and I would just state the it should be only a function of m and n. So it should, okay, so I should simply write f of m n. It should okay, I should not use the term f, I should use the term g. G is some function of mn. What are kind of functions of mn? Maybe m times n is a function of mn, m squared n, mn squared, n cubed is a function of I mean it is a function of m and n, but you cannot have something which is f star, that is the value of the flow into mn. And why is this a bad running time? I mean, so my claim is that this is not a polynomial time algorithm. So do you understand what is a polynomial time algorithm? So currently we have seen some algorithms which is BFS, DFS, we have seen shortest paths, we had seen yesterday all pair shortest paths. All of the algorithms, actually BFS and DFS were simple because there were no edge weights, right? But in shortest paths we certainly had edge weights, but our algorithms did not have in their running time the function a parameter which captured the edge weight, right? It did not require any it did not depend on what is the largest edge weight in the graph, or what is the shortest path in the graph, what is that value and so on. It did not have a parameter. On the other hand, this term is slightly different. It says that what is the max flow in the graph, and that is going to be determining the running time of the algorithm, right? So let me ask, what can be the maximum flow in a graph if you know the capacities? So let us say that I also give you that capital C is the maximum capacity of any edge in the graph. What can you say about the max flow? So actually you can have something like n over 2 vertices adjacent to not n minus 1 vertices adjacent to S, and each of them have capacity C, and then it goes like this, right? Again capacity C to T, in which case you have n minus 1, n minus 2 into capacity capital C as the max flow, right? So the max flow is bounded by O order of n into C, right? And we are saying that this term has a, I mean this thing has n into C into order m plus n, where the maximum capacity is coming as a parameter in the running time of the algorithm. But such a thing did not happen for Dijkstra's algorithm or all pair shortest paths algorithm that we studied. There also there is a edge weight, very similar to capacity. What we interpret that number is a different thing in different contexts, but we still have a number associated with it. Why is this not a good running time? I mean anyway there is just one C times something, right? So what do we understand when we say that some algorithm is an efficient algorithm, or it is a algorithm which runs in polynomial time? What is the polynomial time in? What do you mean by input? Yeah, so the size of the input is the correct term. So what do you mean by the size of the input? But doesn't the input contain your capacities? I mean, can somebody just give you the number of vertices, number of edges? Is that all? Will you be able to run your max flow algorithm? Exactly, that is equal to the number of edges exactly, but that is not what is, so won't you need the capacities themselves? You will need that, right? So the input does contain the capacities, right? But let us now observe the following, that if you wanted to give me n vertices, you have to give me those n vertices and the n edges. But if you wanted to just give me one number, which is the capacity of an edge, let's just talk about one capacity and ask what is how many. So let's take a small step and ask, to represent one number c, how many bits do you require? Log c, right? So if you wanted to represent a number c, you require log c bits, right? And this log c is, so log c into m is actually also coming up into the input size. So you have m edges, you have n vertices, and you have log c many capacity, m many capacity values, each of which take log c bits, because c is the maximum capacity and any capacity can be represented using log c bits, right? So it would have been, I would have been okay if the running time of my algorithm was n times log c times some m plus n or mn or m squared n or something. It can be a function which is log c, it should be a function which takes m, n and log c and can be a polynomial of this. But remember that c is actually equal to 2 to the power log c, and therefore this is not, so this algorithm which we have written down, the running time, is not a algorithm which runs in polynomial time in the size of the input, it runs in exponential time in the size of the input. And this is something which you can think about at several places. For example, you may have thought about primality testing. It's a big problem. And why is it a big problem? Because the simplest algorithm that you can come up with will take time which is order c, again if you wanted to test if c is a prime, but that is not a polynomial time algorithm, again using the same logic, right? And this point is something which is important, that this algorithm is not a polynomial time algorithm, but there are polynomial time algorithms for computing flows, and that you will see when in the next week or maybe in the upcoming lectures.